In this session, I'm going to be talking about how you can write a Spark connector to an external real-time distributed database using the Data Sources API, and also explore the limitations and potential future of the API. How do I go next? Okay, so here's an overview of the topics I'm going to talk about today. First, I will give a high-level overview of how the Data Sources API works. Then we will learn slightly more advanced techniques of the Data Source API to gain various performance benefits. And finally, I will discuss an experimental technique we tried out in the past for MemSQL Spark connector to address some of the limitations of the Data Source API. As for me, I'm a relatively recent graduate of MIT where I explored a framework to share work between Spark queries for my master's thesis. I've been a software engineer at MemSQL for over a year, and one of my projects was to update the MemSQL Spark connector to work with Spark 2.0. So first, a description of the Spark Data Source API. We will first address each of the following topics briefly, and don't worry if the bottom three don't make sense yet. So what is the Spark Data Source API and how does it work? The Spark Data Source API allows Spark SQL to interoperate with external systems such as a distributed database. Spark natively allows you to create a data frame from a hard set of sources. You might be familiar with like xc.txt file that all the tutorials start out with, or using a CSV, but you might have your data stored in a different source. If you implement the Data Source API, you can tell Spark how to create a data frame from a custom data source. So, for example, if you went to sparkpackages.org, you'd see lots of Spark connectors written by software engineers of various data storage solutions. And this is basically like the goal. Once you implement a custom data source connector and package it up, users can import your connector and load data using this syntax. The Spark configuration contains any configuration options the connector requires, and you should generally document this in the README of your connector. So for example, the MemSQL Spark connector requires the host IP of the MemSQL master aggregator. Then you can just write spark.read.format with the package name of your connector and any options the connector requires to load this data frame. For example, here, we're using the MemSQL Spark connector, and this connector takes a path option that specifies the names of the database and table you're loading from. So now that we know the utility of the Data Source API, I will describe how it works. It leverages Spark SQL's Catalyst optimizer. So the way Catalyst works is a Spark SQL statement or a sequence of transformations on a data frame gets parsed into a query tree. And Catalyst just refers to a library of classes that transform these trees. So Catalyst will convert your logical tree, which is an abstract representation of your query, into a physical tree, which you can actually walk through and execute. And when you implement the Data Source API, all you're basically doing is providing Catalyst with a logical node abstractly representing your external data set and a corresponding physical node that can be used to execute, that can be executed to query the external data source. So next we'll have a diagram of how this works. So for the Data Source API, the logical nodes that represent the external dataset use the class called base relation. The base relation node in your logical query tree can represent the table foo, which exists in your database. Then there is a conversion step supplied by your connector to obtain a physical node, also known as an RDD. The RDD actually holds the code to materialize the data from foo. For example, by running the command select star from foo against your database. Next, we will go through the three components in more detail. So we'll start with the logical side of the Data Source API, aka the base relation class. If you write your custom data source connector, you must implement the abstract class called base relation. So Catalyst treats your base relation node in the logical plan as a representation of a table that exists in your external database. So the defining behavior of base relation is that it must be able to produce its schema in terms of Spark types. This allows Catalyst to perform logical optimizations to the logical plan that require it to know its column types. So if you're making a Spark connector for a SQL database, one way you might calculate the schema might be to send a select limit 0 query against the target table and map the return column types into Spark types. So next, we will talk about the conversion step. So we've provided Catalyst with a logical node for a custom data source. Now we need to tell it how to transform it to a physical node. You do this by modifying your aforementioned base relation class to extend one of the scan traits, such as table scan, prune filter scan, catalyst scan, etc. But these all require you to implement the build scan method, and the build scan method returns an RDD, i.e. a physical node. So finally, you have to write a class for your physical nodes, which can actually retrieve the data from your external data source. You can subclass the RDD, which represents a partition data set, and provide a compute function. A compute function is called on each partition to materialize disjoint parts of the table, and together the partitions materialize all of the table. So you should implement your compute function to be specific to your data source. For example, if your external data source is a SQL database, your compute function probably leverages some sort of JDBC driver. If your data source is a file, your compute function might read from the file system. So now I've talked about the basic steps to implement a data source API, from it being parsed by the Spark SQL parser as a logical node, to its conversion to a physical node, to its execution to actually retrieve the data. Now I'll talk about two techniques to improve your data source connector for distributed databases. The first technique is called RDD Partition Pushdown, and the second is SQL Pushdown. So let's go over a quick reminder of the distributed database topology. Here's a diagram of the MemSQL distributed database architecture, but there are common themes throughout a lot of different architectures. So here we have leaf nodes that store different partitions of the databases, and an aggregator that interacts with clients and aggregates the data from leaves when executing queries. So RDD Partition Pushdown is an optimization that becomes most obvious when your MemSQL cluster, or when your distributed database cluster and your Spark cluster are running on the same machines. If your distributed database is partitioned, you can map Spark partitions to database partitions in order to avoid network latency and increase parallelism. So here we have a Spark partition for each database partition, and they are all running in parallel and only transferring data locally. So we do not want a Spark partition reading from a database partition in another machine, as shown in the diagram, because this has to go over the network. We also don't want a mismatch between the number of partitions, because then there's an opportunity for parallelism we aren't taking advantage of. So to get the ideal behavior, you would override the get partitions and get preferred locations methods in your RDD class. So the Spark engine will assign Spark partitions to machines optimally. This is a little verbose, but basically, get partitions allows you to define an arbitrary number of partitions, and get preferred locations is a way to map partitions to executors. So The second optimization for distributed database data sources is to have your database perform any filtering and column selection before it sends the data to Spark. In this example, the user creates a data frame from a table called students in the Hogwarts database, but then they apply a filter only for students who are in Gryffindor, and in the end, they only want their names. So if you implement the data source connector the way we've described so far, your database will load the entire table into Spark, and then the filtering and column selection will be done in Spark. So here you see like the database is loading all of this large table into Spark, but in the end, the user only wants like the data set shown as the yellow rectangle. So when your data source is a SQL database, you can have your database efficiently do these operations instead, and then you're also greatly reducing the size of the data being transferred. So now the data set being sent to Spark is the goal data set. So in order to implement this functionality, you should make sure your base relation extends the trait prune filter scan. So before, when I talked about the conversion step, I mentioned that you just needed to implement one of the scans. But if you implement the prune filter scan in particular, this allows your connector to access a list of columns and filters that the user eventually applies to their data frame. So on the left side is the Catalyst logical plan if you only implement a basic SQL table relation. It plans for Spark to do the select and filter. However, if you implement a better SQL table relation, Catalyst knows that your data source will take care of these operations, and the work to be done in Spark is much simpler. So I guess this gets a little hairy again, but I'll show how the code differs in basic SQL table relation and better SQL table relation. So in basic SQL table relation, which only uses the basic build scan with no arguments, we don't have any information about filters and can only return an RDD that will eventually execute the SQL query select star from database.table. However, in better SQL table relation, our build scan has a different signature, and it is run with the arguments required columns and filters. So with this information, we can instead return an RDD that will execute the more encompassing SQL query of the form select columns where the filters are true from database.table. Okay, so now I'm going to try to show you a demo. 1 second. Okay, so it looks like this is already running. Can I change this to mirrored? Okay. Okay, so I have here like hooked up a Jupyter notebook to run with PySpark, where I've loaded in the MemSQL Spark connector. And I also have like a 2-node, it's relatively small, just a 2-node MemSQL cluster running on the same machines. And I've loaded like, I think just 1 gigabyte of the TPCH data. So here I'll show you like a small benchmark function. It takes an arbitrary function, and we run it once to warm up the cache. And then we run it as many times as we can in 20 seconds, and we take the average execution time of all of those runs. Oh, okay. Okay, yes. Yeah, so we're going to be leveraging this benchmark function where we warm up the cache and then run it as many times as we can for 20 seconds. Okay, so if you want to kind of look at the shape of the data, I think I have show. Oops. So our databases here are like, the first three have to do with MemSQL and they're used for clustering, but we'll use tpch, show tables. We have these selection of tables, and we can kind of look at the line item one, look at its shape. Okay, so it has like these various columns, including one called quantity. So what does that sort of look like? Select L quantity from line item limit 30. Okay, so these are approximately the various values that you'll see. They seem to be between like 0 and definitely 100. Okay, so in our notebook, my demo is basically going to be comparing the MemSQL Spark connector, which was written with the MemSQL topology in mind, compared to Spark. It is shipped with a JDBC data source connector, which can connect to just like any arbitrary SQL database. But this also means it has to be agnostic to all of the various database topologies. And you won't have like optimizations like RDD, partition pushdown. Okay, so this is going to, the first one, we use the MemSQL Spark connector, and it takes, and we're reading from tpch.line item, and we're going to filter for else underscore quantity is less than 30. And then we're going to do the same thing with the JDBC connector. So I run this, and it will take, oops, I forgot to run the second one. Run. Okay, so this will take 40 seconds because it has to do 2 benchmarks where I'm just running it for 20 seconds. Yeah, but I guess I'll talk a little bit more about, so I've described how the MemSQL Spark connector uses RDD partition pushdown, and so it's going to have one partition for every MemSQL database partition, and you get a lot of parallelism. But if you actually went into the JDBC data source code, you'll find that in the general case, which is what's happening now, there's only one partition. So all your data is being filtered through one partition and one executor, and there's not really any parallelism. Like the best attempt at partitioning the JDBC partition, or the JDBC data source lets you do is kind of like choose a column, and then it will slice the data up using where statements so that every partition gets a disjoint part of the table. But you can imagine that this is not very good for data locality because like your segments where the column values between like 10 and 20 might still all be on different machines. Okay, so yeah, so we have this comparison where the MemSQL, like the custom Spark connector for MemSQL, because it's very knowledgeable about the internals of MemSQL, it only takes 1 second, but the architecture agnostic JDBC connector takes twice as much time. And this is a relatively small data set. I think you'll see that the difference grows as you grow like the cluster size and the data set size. I actually tried this on a 4-node cluster, right? Like I was preparing to demo this on a 4-node cluster, but then like after the MemSQL query return, the JDBC one would just and I thought that was an even worse like viewer experience, so I scaled it down to a 2-node cluster, so at least you see a number for the second one. Okay, so back to the talk. Okay, so that was the demo, and then, oh, wait, sorry. Okay, so however, the data source API as it currently stands still has some limitations, but first we should have some context on how joins on distributed data work. So joins can be implemented several ways. One method is the default sort merge join. Here you require that rows with the same join key range of both tables end up on the same machine to perform the join. So this generally means that you have to shuffle both data sets across the network. The broadcast hash join is an optimization if one of the data sets is small enough to fit into memory. You can then copy that small data set to every node, and then the joins can be computed locally and in parallel. So here is a diagram of the first one, the sort merge join, and how each machine potentially has to send rows of its table to every other machine to get rows of the same key range on the same machine before the joins can proceed. I kind of tried to label it with like numbers, so the join key ranges from 1 through 8. And in the end, you need them to be sorted, so you can do like the join where you keep track of the index on each table and then you just like walk it down. But so you could be unlucky and you don't have like the right keys on any machine, so this would require a cluster-wide shuffle. Alternatively, here's a diagram depicting broadcast hash join, where you only have to broadcast the smaller table, and then the joins can proceed in parallel. So if the table is small, broadcast hash join represents a large optimization. But the problem is that Spark SQL will not optimize joins if the data comes from the data source API. So I have another, I know we just went through a demo and it had a lot of overhead, but this one also has a demo. Okay, so let me go to, I'll just start screen sharing. Okay. Yeah. Thanks. What is this? Did I think I might have set up SSH port forwarding here, so it's, yeah. Okay. Oops, wrong one. Okay, so I'm starting up an interactive Spark shell. Yikes. Oh, oops. Actually, I'm gonna make it smaller while I put in credentials. Okay, so also prior to this presentation time, I loaded the same TPCH data that's in MemSQL into HDFS in the Parquet format. So we're going to see what happens with joins from Parquet, which is supported natively by Spark, versus MemSQL Spark connector, which goes through the data source API. So first we will create a data frame from the table nation, which is a small data frame. So you can, after this finishes, we can do Parquet nation.count, and it's small. Also, to be convinced that we have the same data. What? Sorry, I don't know what happened there. This is the same size. And then we will also put in the Parquet customer table, which is large. And we can see how many records are here. It's sort of large. It's large enough. Okay, so we can look at the execution plan for the join on the key that they share, which will be nation key. So Parquet nation.join Parquet customer on. So for Parquet nation, it's n nation key equals c nation key explain. Okay, so Spark natively knows the size of the tables, so it's going to plan for the join to be this broadcast hash join because nation is small and customer is large, so this is the optimization that we talked about when we talked about the different types of joins. Now we're gonna get those exact same tables, but like the quality of the table is exactly the same, the shape of the data, the size of the table, but it just comes from a different source. So this one is memSQL nation, and we will do memSQL customer. And okay, so now we will also get the join explain. Okay, and the result you see is a sort merge join. In particular, it scans the table, so the sort merge join means it has to do a sort, but the sort is on a distributed data set, which means it has to do a shuffle. So this is not optimal. All right, so back to the slides. So we saw that Spark will not do the optimization if the data source comes from the data source API. And so this makes sense because in our implementation of our connector, you recall that we never actually calculate the table size. We never provide a way for the Spark Catalyst optimizer to know that one table is small and one is big. So actually, the base relation class does have a function called size in bytes that you can override, which would provide Spark with this information. But custom data sources almost never provide a way to calculate this because size in bytes will be called multiple times by the Spark query planner, and this could be quite expensive. So the best solution would be to somehow get memSQL to perform the join, which also has a query optimizer with optimizations for joins. So let's think about how we can modify Catalyst to push down the join into our distributed database. First, we'll recall the basic steps of Spark SQL again. So first, the parser creates a tree representing a logical plan of the query from the user's code. Then the Catalyst optimizer simplifies parts of the logical plan and obtains a final logical plan. Then Catalyst transforms the logical plan to a physical plan that can be executed. So in the Catalyst library, the classes that do this logical to physical transformation are called strategies. So in the figure, various strategies translate a logical aggregate to a specific implementation of aggregate, as well as for the join, and the base relation become RDDs as written by our data source API. So here is the Spark code that shows the concrete strategy Spark has. As you can see, there is a data source strategy, which is where our data source API plugs in. So when we wrote the first memSQL Spark connector, we tried adding in our own strategy in order to push down joins. So the data source strategy, the one that already exists in the Spark planner by default, only replaces logical MemSQL table relation nodes with the corresponding physical MemSQL RDD. In our new MemSQL strategy that we added, we intercept logical subtrees of join nodes into MemSQL table relation leaf nodes, and we try to collapse the join in this way. So this happens before the data source strategy. And we end up replacing the whole subtree with one single physical MemSQL RDD node that will perform the join in MemSQL. So being able to add custom pattern matching rules for Spark by adding your own strategies seems like a powerful idea, but custom strategies is still unsupported and not a public-facing API. It's currently labeled as unstable, and thus for the release version of MemSQL Spark Connector, we decided to remove the experimental custom strategy. Instead, we wrote our data source API so that Spark SQL users could load data using a query instead of just a database and table name. Now we encourage users to explicitly write in their join when loading data from MemSQL. I was just looking at the Spark Jira earlier this month and found that improvements on the data source API is active and ramping up. The listed Spark ticket contains all the discussion for the next iteration of the data source API based on community feedback. And its target version is 2.3.0, which is the next version. You should take a look if today's talk gave you any ideas. Thank you.